You think you know what cutting-edge architecture looks like? These Chinese structures prove China's architecture is 100 years ahead of anything you've seen. We're not talking about concepts or renderings. These are real buildings, standing right now, that solve engineering problems the rest of the world hasn't even figured out how to ask yet. Structures that bent the laws of physics, rewrote the rules of construction, and made the impossible routine. And it starts with a building that looks like it grew out of the earth itself. Harbin Grand Theatre. The Harbin Grand Theatre doesn't sit on the landscape, it becomes the landscape. You're looking at seamless aluminum panels flowing across curves so smooth, so organic, that engineers said it couldn't be built with traditional methods. But here's the problem. Organic shapes like this create structural nightmares. Every curve changes the load path. Every surface needs custom engineering. The solution? A hidden structural framework that allows completely column-free interior spaces, massive performance halls with zero obstructions, all while the building appears to ripple like frozen water. The exterior panels aren't just aesthetic, they're part of the structural system, each one calculated to handle snow loads that would crush conventional roofs. And somehow, they engineered this entire impossibility on wetland terrain without compromising the foundation. But that was just playing with curves on land. Beijing National Aquatics Center. What happens when you try to build water itself? The water cube answered that question with ETFE cushions, a material lighter than glass, stronger than you'd believe, arranged in a pattern copied directly from water molecules. Here's where it gets insane. Each bubble is a structural element. The building doesn't have a traditional facade, it has a self-supporting bubble wrap that holds itself up while letting light flood through. These aren't decorative pillows stuck to a frame. The ETFE cushions are the frame. They're self-cleaning, they capture solar energy, and they create an interior that feels like you're swimming inside light itself. Engineers had to invent new inflation systems, new joining methods, new everything, just to make molecular geometry buildable at this scale. And this was back in 2008. But if bubbles seem wild, wait until you see what happens when you carve stone that isn't stone. Guangzhou Opera House. Zaha Hadid looked at two boulders by a river and said, "Make that out of concrete." The Guangzhou Opera House is double-curved concrete surfaces that defy every rule of traditional forming. You can't pour concrete into curves like this. You can't calculate the formwork. You can't predict how it'll set. But they did it anyway. Here's the tension. Inside those impossible curves, you need perfect acoustics. Concert hall acoustics are already brutal to engineer in regular, rectangular rooms. Now try it when every surface is curved, when there are no parallel walls, and when the entire shell is cantilevered out over empty space. The structural ribs supporting these cantilevers are hidden beneath the surface, each one custom calculated because not a single angle repeats. They built a building where every square foot required unique engineering, but at least that one's on solid ground. Zhuhai Opera House. The Zhuhai Opera House takes that same impossible geometry and suspends it over water. Two shell structures that look like they washed ashore, cantilevered out over the coastline, each one defying gravity in a different direction. The engineering problem compounds. Now you're not just fighting gravity, you're fighting typhoons, saltwater corrosion, and seismic activity on an island. The steel framework hidden inside those smooth shells has to flex with earthquakes while staying rigid enough to support massive cantilevers. Every connection point had to be waterproofed. Every surface had to resist coastal erosion, and the whole thing had to look effortless. But shells over water were just the warm-up for what Beijing did with steel. Beijing National Stadium, 42,000 tons of steel, twisted into what looks like complete chaos. The bird's nest isn't random, it's the opposite of random. Every single beam in that crisscrossing lattice was calculated for optimal load distribution. Here's the nightmare. Traditional stadiums hide their structure. This one makes the structure the entire design. Which means every weld is visible. Every connection is exposed. There's nowhere to hide mistakes. And then, the real problem. You need to integrate a retractable roof into a seemingly random pattern of steel. The lattice had to be strong enough to support 100,000 spectators, while looking delicate enough to appear woven by hand. Engineers spent years running simulations just to figure out which beams could be removed without collapse. They eliminated entire tons of steel, making it lighter and more complex simultaneously. The result? A structure that breathes, that moves with temperature changes, that survives earthquakes by flexing instead of breaking. But that's still just one building with one shape. Galaxy Soho said, "Forget shapes entirely. Forget floors. Forget corners. What you're seeing is a continuous flowing surface that eliminates traditional floor plates completely." The engineering problem is immediate. Buildings need floors. Floors need columns. Columns need to stack vertically. Galaxy Soho has none of that. Instead, it's got flowing, column-free spaces carved out of solid volumes. The structural system had to support floors that curve, that merge, that don't align between levels. Courtyard voids are carved through the building in impossible positions, which means loads transfer diagonally, horizontally, every direction, except straight down. And here's the kicker. It all had to be built with conventional construction methods. They couldn't wait for future technology. They had to make the future buildable right now. But if you think flowing curves are complex, wait until you see what happens when every single panel is different. Xi'an Cultural Center, 30,000 unique panels. Not similar, not close, unique. The Xi'an Cultural Center's parametric facade means every single piece of the building's skin was custom fabricated, custom calculated, custom installed. Here's why that's insane. Traditional buildings repeat. Same window, different location. Same panel, different floor. Repetition makes buildings affordable. This building said no to all of that. The structural diagrid underneath had to support organic forms that change shape as they rise. Climate-responsive engineering meant each panel had to perform differently based on its orientation, its height, its sun exposure. And the whole thing had to look seamless, like it grew that way naturally. Engineers didn't just design one building, they designed 30,000 individual solutions that somehow work as one. But at least those panels stayed flat. Wangjing Soho. Wangjing Soho has 3 towers with 0 parallel walls. Not one. Every surface curves. Every floor plan is different. The structural cores, the spines that hold these towers up, had to curve with the buildings, which means they're resisting lateral wind loads on surfaces that are already leaning. Traditional cores are straight because straight is strong. These cores twist, and they still had to be stronger. Then there's the glass. Continuous curved glass skin wrapping compound curves. You can't manufacture flat glass and bend it into these shapes. Every panel had to be calculated for its exact position, its exact curve. And all 3 towers had to be engineered simultaneously because they lean toward each other, creating wind patterns that affect all 3 at once. But those towers only twisted in one city, Sanya's new harborside cultural district. Sanya took that complexity and threw it into typhoon territory. Multiple performance venues, each one cantilevered over water. Each one engineered to survive 100-mile-per-hour winds while maintaining perfect acoustics inside. Here's the problem. Typhoons create uplift. They don't just push buildings sideways, they try to rip roofs off. So these cantilevered halls hovering over the coastline had to be anchored down while appearing to float. The structural system integrates environmental controls directly into the framework. Natural ventilation, solar shading, rainwater management, all hidden inside shapes that look purely sculptural. And every surface facing the ocean had to resist saltwater corrosion for decades. They weren't just building for opening day, they were building for the next century of storms. But even typhoon-proof cantilevers pale compared to what happened in Beijing. Leeza Soho, 194 meters of empty space, straight up through the center of a tower, the world's tallest atrium. And here's why that's terrifying. Atriums are voids. Voids don't support weight. But this building is split in half by that void, which means the 2 halves had to support themselves independently while being connected by sky bridges. And then they twisted it. The entire structure rotates as it rises, transferring loads through the twist itself. Engineers had to calculate how forces move through a building that's actively changing shape vertically. The sky bridges aren't decorative, they're structural ties keeping the split halves stable. Remove them and both halves collapse. Every floor plate is different because the rotation never stops. They turned a void into a structural element. 1. This rage. But if a void can hold up a tower, what happens when you carve voids through everything? Tianjin Binhai Library. A 33-meter span with 0 columns, and right in the middle, a sphere floating in space. The eye isn't sitting on anything. It's suspended in the void, an auditorium hanging in the center of the library, while terraced bookshelves flow around it like waves. Here's the engineering nightmare. Those terraces aren't just shelves, they're the structure. Each wave is a load-bearing element supporting the floor above it, while appearing to flow continuously. The sphere had to be light enough to suspend, but strong enough to hold hundreds of people. And the whole thing had to be built before the bookshelves went in, which means the structure supported itself during construction in a completely different configuration than its final state. They engineered it twice, once for how it builds, once for how it lives. But that's still one building with one function. Bund Finance Center and Fosun Foundation. Shanghai took a historic facade and built the future on top of it. 3 draped metal veils suspended from a structural frame, hanging over a preserved building that's a century old. The engineering paradox is immediate. The old building can't support new loads, so the new tower doesn't touch it. The veils suspend from a completely independent structure, hovering millimeters away from the historic facade. Triple-layer climate engineering means the draped metal isn't decorative. It's part of an environmental system, managing heat, light, and airflow between the layers. And here's the precision required. The modern structure had to be built around the old one, without disturbing foundations that were laid before anyone knew what a skyscraper was. One miscalculation, and the historic building collapses. They threaded the future through the past. But threading is delicate work compared to carving. Morpheus Hotel. They carved voids through 40 floors of a standing building. Not windows, not atriums. Freeform voids that tunnel through the Morpheus Hotel like someone took a sculptor's tool to a skyscraper. Here's the impossibility. Buildings need continuous vertical structure. Columns stack. Cores run straight. You can't just carve holes wherever you want. Except they did. The exoskeleton wrapping the outside isn't decorative. It's the only thing holding this building up. Every interior column was eliminated. The entire structural load transfers through that external skeleton, which had to be strong enough to bridge over the voids, while flexible enough to handle wind loads on a shape that catches wind from every direction. And those voids? Each one required structural optimization through advanced computation that didn't exist a decade earlier. They had to invent the software to calculate whether this building would stand. But at least it's a rectangular tower with holes. What if the entire tower was the hole? Guangzhou Circle. A 48-meter diameter void, perfectly circular, punched through the center of a skyscraper. The Guangzhou Circle is a structural ring, distributing massive loads around emptiness. Traditional towers transfer weight straight down. This one transfers weight around. The cantilever required to span that void shouldn't be possible. The upper floors are hanging over nothing, held up by a ring structure that's also supporting everything above it. And then seismic engineering. The building has to move during earthquakes, but circular structures don't flex the same way rectangular ones do. They had to engineer damping systems into a shape that defies conventional skyscraper logic. Every floor plate is a massive ring, each one engineered to tie into the one above and below while maintaining that perfect circle. 1 degree off and the whole thing destabilizes. But if one circle breaks physics, what about multiple petals? Hangzhou Olympic Sports Center. Each petal of this lotus spans over 100 meters. Not supported in the middle, cantilevered from the edge. The cable net structure creating the flower geometry is holding up a roof that covers an entire Olympic stadium while appearing to float on air. Here's the tension. Cable structures are flexible. Stadiums need to be rigid. These petals had to flex enough to handle wind without flexing so much that they bounce during events. The integrated stadium bowl and shell structure means the roof isn't separate from the seating, they're one continuous engineered system. Forces from the roof transfer into the bowl, forces from the bowl stabilize the roof. And every petal is identical, which means if one fails structurally, the symmetry of the whole system collapses. They engineered redundancy into a flower, but those petals are permanent. What if you built something complex, knowing it would melt? Harbin Ice and Snow World. Ice as primary structure. Not steel with ice decoration. Not concrete with ice cladding. Load-bearing ice walls. Ice columns. Ice arches spanning distances that would challenge concrete. Every year, they build a city out of frozen water, engineer it to hold thousands of people, and then watch it melt. The structural calculations are brutal. Ice strength changes with temperature. A wall that's stable at -40 degrees fails at -10. They're engineering for a moving target, calculating loads for a material that's actively weakening. And the scale is monumental. Buildings 6 stories tall, made entirely of ice blocks, lit from within, structurally sound enough for occupancy. It's temporary architecture at permanent scale, rebuilt every year with new designs, new engineering challenges, new solutions to the same impossible problem, making winter itself buildable. But ice melts. What if you built something that floated? National Center for the Performing Arts Beijing, a titanium and glass dome spanning over 200 meters, sitting in the middle of an artificial lake with the only entrance underwater. The engineering problem starts with water pressure. This dome isn't just spanning huge, it's resisting lateral pressure from a lake that's actively trying to crush it. The shell structure had to be watertight at every seam, because one leak doesn't just damage the building, it floods the entrance tunnel where thousands of people walk beneath the lake. And here's the paradox. Domes are strong because they're symmetrical. This one has a massive opening cut into it for the underwater entrance, which destroys the symmetry. Engineers had to reinforce the opening without making it visible, maintaining the perfect egg shape while compensating for the structural weakness of the cut. The glass panels aren't flat, they're curved to match the dome, which means every single piece is custom, and the whole thing sits on shock absorbers because Beijing gets earthquakes. A floating dome, engineered to move with the earth while keeping water out. But that dome serves one purpose. What if you made architecture that served none? Marisfrolg Pavilion. A pixelated, fragmented exterior that looks like a digital glitch made physical. The Marisfrolg Pavilion proved that small-scale experimental architecture could be just as structurally insane as the massive projects. Here's the challenge. Every pixel is a module. Every module is slightly different. And every module has to be structural, weatherproof, and precisely positioned. The modular system creating this complex geometry meant fabricating hundreds of unique aluminum components, each one engineered to connect at different angles. There's no repetition to fall back on. No standard details. Traditional buildings scale up simple solutions. This one scaled up complexity itself. The structure had to support fragmented forms that appeared to defy gravity, cantilevered pixels jutting out at impossible angles, held in place by a hidden framework that's doing calculus at every connection point. They took parametric engineering and made it touchable, buildable, real, and somehow made it work for retail space, which means it also had to be affordable. You've just witnessed 17 buildings that rewrote structural possibility, ETFE bubbles that self-clean, voids carved through standing towers, ice engineered to bear loads, domes floating on lakes, 30,000 unique panels, 194-meter atrium splitting a building in half. These aren't concepts waiting for future technology. They're standing right now, occupied, functional, proving that the future of architecture isn't coming, it's already here. China didn't just push the boundaries of what's buildable. They deleted the boundaries entirely. This is what 100 years ahead looks like, and you're looking at it today.